I have always had huge admiration for the author of this book. And I've been, I guess, one of these days I thought I would have the author come and visit our lab. And my dream has come true. And actually, the author is here. And it's sort of like my dream has come true. And I'm really, really grateful. I also wish that you are, grateful for his presence here. I think, by interacting with him, I think you will be inspired, and hopefully it will help you with your current research. Okay, let me just introduce. I know he gave a lecture. Was it yesterday?
Yes.
Yeah, yesterday. A great lecture yesterday, and he'll be also giving one tomorrow. Let's really give Shai Ben David, sorry about this. David, a great warm applause.
Okay.
And let's welcome.
Thank you. I would really like to have some kind of more informal discussion. I also have a presentation. I have many different topics that I can talk about, we have to talk about. So tomorrow I will talk about fairness, and today I wanted to talk about clustering, but I also wanted to respond to some of the talks that you presented yesterday. So the day before, on Monday. So yeah, so I'm saying that what I meanwhile I wanted to make you aware of is that there is this paper that I will share with you that is not published yet. It's my a colleague of mine. She was my ex-PhD student, and it tries to see take a high-level approach to what is calibration. And so, what are the desired properties that we want from calibration, and how can we handle it? Because people use calibration, but I think it's lacking kind of what is it used for, what do we want to get. So we assume that we have some ground truths, which is, usually we talk about the probability P over X cross Y, where X is your domain space, your instances, and Y is the labels. And if Y is just binary, then we can talk about this, we can split P into two components. So I can say that P is actually the projection on the space X times this labeling rule eta, which gives me for every X the probability of Y equal 1, given the SX. So we can split the probability distribution into the probability of seeing instances, and given an instance, what's the probability of the label that we will see. Well, that's if it is binary prediction, or if it is real valued, then eta is just the regression function. Okay? So this is the ground truth. And now we have a function which is our the function that we learned, which is, so we learn, we have hypothesis f, which goes, say, from x to the unit interval. That's what the object that we talk about when we talk about calibration. And what do we mean? What do we want from f to be? So the calibration function, we want it to be a function that gives us a prediction of the label, but also gives us some confidence about this label, right? So this is my function f that now I want to say that f is calibrated. What are the requirements that I want from such an f that I hypothesis? So the requirements or the desired properties for a calibration. So the first thing, of course, is the definition of calibration. So the definition of calibration, we want that for every x, we want that the expectation, so we want that for every value x, we look at f of x, and we want the expectation of pairs x, y that y equals 1 given f of x. We want this to be f of x, right? Did I write it? I mean, I hope I didn't make it.
That expectation is, I think it's over probability. The probability of
The
given f of
probability,
x,
okay.
probability of given f of x, which,
Probability given f of x that y equals 1 is
1
going
equals
to be
the f of x. Is that right? Is that right?
Yes. If it's 0 or 1, then it's the same as the
Yeah,
expectation.
exactly.
And okay, so this is the first thing that we want, but we want some other properties as well. So, for example, we want to be able to predict with this f. So we want that there exists some threshold phi such that if I predict with the function f phi, which is 1 if f of x is greater than phi and 0 otherwise, I want this function to be a good predictor. Right? I want this f to allow me to do a prediction of the 0, 1 label. So I want that there exists a phi such that if I threshold there, I get a good predictor. So then what does it mean, a good predictor? That LP of f phi is as small as possible. Right? LP is the probability over x, y that f phi of x is not equal y. The probability that I make a mistake, I want it to be as small as possible. I want to use this function. This is telling me that the function gives me kind of the confidence. But this tells me that the function is useful for predicting the label.
What is the relationship between f of x and f theta that you have right here? Is the same
Okay,
thing? Or?
so f theta is what I defined here. F theta is thresholding f at theta.
Okay.
So it's 1 if f of x is greater than theta, and it's 0 otherwise. If you want to...
We're looking at only the binary case.
We're looking at the
Binary case, only the binary
case. If you want to look at f as estimation of the base predictor, then we will take theta to be a half. Right? If you have the base predictor, then it is the function that gives you 1 if the probability of seeing 1 is greater than half, and 0 if the probability of seeing 1 is less than half. But we can be even more flexible and say there exists some threshold. So that's kind of a different requirement. This is the requirement that tells me that f gives me the right confidence, but this is the requirement that tells me that f can be used to give me the correct label, or the best possible label. And I can think of more requirements which are I would expect from this function f. So for example, I would like to have monotonicity. So what do I mean by monotonicity? I want to look at the probability. I mean, when does monotonicity, when is it violated? It is violated if I have in my domain two points, say x and x prime, such that f of x is greater than f of x prime, but the real probability eta of x is the other way around. That eta of x is less than eta of x prime. If I have such a violation that x has a higher probability of getting 1, but my function f gave it a lower value. Does it make sense? I want that my function f increases with the probability that x will get value 1. So how can we formalize it? Intuitively, I just want you to agree that, or ask if it's not clear why we want monotonicity. F is I want that my confidence that the label is 1 will be higher if indeed the probability of seeing 1 is higher. You see, eta is that ground truth. We don't know eta.
So if they are the same, will it be perfect in front of you?
If they are the same, that will be perfectly calibrated. But we cannot guarantee that they will be the same. We will get to this requirement in a minute. Right? So how can I write this monotonicity? I can write it as saying that the probability, I can write it as saying that the probability over x and x prime, so x and x prime, that I sample from px, remember px is the marginal, is the projection on x, so I sample 2 points. I want that the probability that f of x minus f of x prime times eta of x minus eta of x prime is less or equal than 0 to be small. You see, this product is positive if whenever f of x is greater than f of x prime, then eta of x is greater than eta of x prime. Or whenever this is smaller than this, then this is smaller than this. So the bad case is that one of them is bigger, but the other one is smaller. The bad case is that the product is negative. So I want that the probability that of this bad case, that I said I'm more sure that x is 1, but actually x prime has a better chance of getting value 1. I want this probability to be small. So that's another requirement, which is the monotonicity of my predictor f. Right? And that's...
So, okay, so let's just take 1 or 2 cases. Let's say you have x, you have 2 situations where eta x is greater than eta x prime. Okay, so that means that
the true probability of label 1 is greater for x.
Also, eta is the true probability.
Right, eta is the ground truth.
Okay, eta is the ground truth that we don't know.
We don't know.
Okay. So let's say if eta x is greater than eta x prime, then x has more probability than x prime of a higher probability. Now, in order to be negative, then you have to have the signs the other way around, right?
So I want it to be negative as fewer times as possible.
Oh, you want that to be small. The probability of that, for that space to be small, like your epsilon, epsilon and eta case. Okay, so okay, I see. Okay, or delta, epsilon, delta. Okay. Oh, okay. So sort of. Okay.
I want this probability to be small, and I can have more requirements. So, for example, another very natural requirement is that the function requirement number 4 could be that the function f is roughly like the function eta. So I can look at the mean square error of the difference between 2 functions, right? So I can look at the integral over x of f of x minus eta of x square, and x is by my probability, and I want it to be as small as possible.
Okay, so we actually have a paper on number 4.
Right, so I'm saying we want all of those requirements.
Okay.
Right? And there are also, I will not get into
I'll just ask one more question. Sorry about this other situation. Let's say you had we're dealing with, multi-class, okay? So how would I set this up, monotonicity in the multi-class?
Right, so the monotonicity...
Can you write it here so that we can all look at it? Because that
so the monotonicity is...
Oh, I'm sorry. Yeah, can you do that just for just a second? Thank you very much.
I will take it up and then we can write the book.
So we've actually done this, right, to Joshua, the 4th one?
Something similar, yes.
Something similar, yeah. So that we wrote a paper on this.
Okay, but so...
And there's a measure called ECE, which is...
approximation of the ground truth.
Right.
Approximation.
So, the question is, in what way do we want to approximate the ground truth? What I'm giving here is kind of different ways in which you want to approximate the ground
That's
truth.
it. So we never
If
thought
I-
about
now-
this, okay, monotones, okay?
So, and sure, monotonicity is in the case that the values are ordered.
Mhm.
If there are categories, then we will have to phrase the monotonicity differently. But this is in the case they are ordered. Say you give me a score for, and the scores do not have to be, I mean, they could be real values, and they could also be the scores, the eta function. What is the ground truth?
Would would 3 be a subset of 4?
No. So what I'm saying is that we can show that these properties are independent. That we can easily construct cases where each of these properties is satisfied and other properties are failed. Of course, if you get exact zero, if f is exactly eta, then everything will be satisfied perfectly. But as long as they're not satisfied perfectly, so let me just give you one example of how can we violate one and not the other. So assume that my probability is very simple. I have only 2 points. And the probability of seeing this point is a half. And the probability of seeing this point is a half. And this point is labeled. So this point has labeled 0, and this point has labeled 1. And the probability of seeing each point is a half. And now if I take f, so let's call this point x and x prime, and this is all that I have in my space. Just 2 points. So if I have f of x equals f of x prime equals half, then what is my calibration here? How am I doing in terms of calibration?
You are doing, I mean,
Perfect.
it's perfect, right?
It's perfect calibration.
Right.
But it's perfect calibration, right? Because f of x equals half happens in both cases, and if I take them together, the probability in that case of seeing 1 is half. So I'm doing perfectly in terms of calibration. But in terms of being able to predict the label, I'm doing terribly. Because I don't have a threshold that will, if I threshold at that point, I will get the label here 1 and the label here 0.
No, what, I mean, that's an instance, and you also have the label for each instance, x, I think you've drawn instances, but in general, you have, for each instance, you have 0 and 1, 0 and 1.
What I'm saying, for both instances, I will have the probability, f will tell me the probability of 0 is half and probability of 1 is half. That's what it tells me. So this function doesn't help me to do classification at all, but it is perfectly calibrated. I can look at another function, say that g of x is some half minus epsilon, and g of x prime is some half plus epsilon. And now it's great for prediction, because if I threshold at a half, then this will give me 0, this will give me 1, I make no error at all. But in terms of calibration, this is very bad. Because in terms of calibration, from all the points that give me half minus epsilon, the probability of 1 is 0. But f gives me half minus epsilon. So this is bad calibration, bad property 1, and good in terms of property 2. And this is the other way around, good for property 1, but bad for property 2. And this we can show that each of those requirements, each of those desired properties, as long as I don't know the exact ground truth, each of them can be violated and others satisfied. They are kind of independent. So when we talk about calibration, we have to think of what are we aiming for. Okay, so I just want, this is just a teaser. There is this paper that I will send it to you. That's the Urner. Ruth Urner was my PhD student, and now she's a professor at York University. And that's a recent paper of hers with a student of hers. I don't remember the name of the student.
Okay.
And they are kind of discussing this and discussing how to fix it and how to trade off the different properties that you want.
Well, so going back to number 3, if you had a multi,
Right, so you have to think of how to do it in terms of
multi-class.
there are categories and they are not ordered. If they are ordered, we can still do the same thing. But if the labels are not ordered, we have to think of a variation of this. And they have another property, because somehow, one of the things that we want that the calibration will be in some way interpretable. And the problem is that here, it gives you, full calibration gives you a probability over all the points that have the same value f of x. But this set, as you remember that when we went in the talk on Monday, I actually told you that the way I view it is you have your space X, and you partition it into cells, and in every cell, you want that F will give you the average value of the cell, the average value of Y in the cell. So in this version, the cells are defined by all the x's that have, so we say x is equivalent to x prime. They're in the same size, in the same cell, if and only if f of x equals f of x prime. That's how we divide it into cells. We divide it into cells by having the same prediction f.
Right, okay.
Right? But the problem is that those cells are very difficult to interpret, because we don't know, how f sends different points to different cells. This conditioning here is very uninterpretable, because it conditions on the function f and not conditions on any property of x. It will be different to say.
So I think the okay.
I can require Lipschitzness. I can require that if x is similar to x prime, then f of x is similar to f of x prime, or something like that. That's more interpretable, because I know about the x's. But here the conditioning is about having the same f, which is something that we don't know how it is happening.
So I would be thinking like this. Okay, so if they're giving, so all these points, instances within that cell are giving you the same prediction, right? Same prediction. That's what it's saying, right?
Right.
So you would have to do some type of analysis, or between the instances that,
Right.
and then you can probably make some.
Right, but if we, yeah, you're right. But what I'm saying is that in practice, say I'm giving prediction to a patient. I'm telling a patient, you have 70% success of your surgery. I'm not looking at it on the basis of all the patients that I will say 70%. I'm looking at it of all the patients that have the same, a patient for me is some blood pressure and age and weight and I don't know what, and what I'm really conditioning is on cells that are defined by this vector, and not all cells that are defined by those that I gave them 70%. When a doctor tells you you have 70% success, he is talking about partitioning the patients according to their input vectors, not partitioning the patients according to my prediction.
We can go on and on for this, but it's an argument. But we don't know, when we make a prediction, we don't know the causality between this and our. But because of whatever the data gives you, it's giving people based on that, are giving you the same labels. So based on that, you can sort of go back and say, maybe some of those features are.
If two patients have the same vector, they will get the same value. But it can also be the case that the same value is given to also a patient with a completely different vector.
This is possible.
This is possible, and then it's less interpretable. Which group are you comparing me to when you tell me that I have 70% success? And you see, I could partition according to to the input vector. But here I partition according to my function f, which is the function that I learned, which is the function that my deep neural network output, which I don't know how the deep neural network decided on this function. So we need here more requirements to make it more interpretable or more accessible.
In this desired property, this wouldn't there won't be any I'm not sure if this is the correct term, but fairness within groups. So it could be well calibrated in subsets. I mean, most
right. I mean, one thing that we can say is that I will divide it according to this vector, but I will also have here some group membership. I want that among the women, the success rate is the same as among the men. Among the young women, so I can say, okay, I divide my space into women and men. And then I divide my space into young and old. And then I divide the space into Caucasian and black. But this is a different partitioning to cells. And in fairness, you're right. In fairness, I want that those cells will have good prediction over the cell. It's not the cells defined by the function f the way we define it in calibration. Okay, so that's my comment about calibration, and I will send you the link to the paper because it was not published yet, but she agreed that I will share it with you.
Oh, great, thank you very much. Yes.
Okay. So that's my comment about the fairness, about the calibration.
Oh, yeah, sure.
Thanks very much. So, you know what, we have a number of students who worked on this and are sort of working something else right now on LLM and diffusion. When we can go back, right, and talk about some more conditions, then I think we can think about this. I think there's a lot of other stuff that we can talk about, okay?
And I wanted now to, before I start talking about clustering, I wanted also to make a comment about your talk, about the
Causality.
Context vision, or how do you call it? Vision with
Scene understanding.
what?
Scene understanding.
Scene understanding, but it was kind of
common sense.
common sense. Yeah, common sense, right. So, yeah, because I thought a little bit about your examples. I mean, you gave two examples. You gave the examples of the dog catching frisbee. You gave the example of the child with the sausage and whether this child is happy or not. And I wonder, I somehow think that those examples are about different issues. So I want to show you some examples of mine and talk about what are these different issues. So,
It's ready for you.
thank you.
You can block it and present.
Thank you very much.
I had this thing I passed in the security at the airport a short time ago, and I left my laptop at the security. You know, they want you to take the laptop out, and you're in a hurry to your plane, and then you realize, oh, I left the laptop there on the conveyor belt, and then I tell them I forgot my laptop here, and they have the laptop, and they tell me that I have to prove that it's mine. So they open it, and I have to put my finger to see if it will unlock. But if your finger is dirty or something, I was a bit tense. Maybe it will not unlock now because my finger is sweaty or something, and then you'll not give me my laptop. Anyway.
So did you, I guess you got it open.
Here it is.
Yeah. Good.
Anyway, so let me go to the slides. And I want to start with this comment on the, before I go to the, okay. So I have here some slides that kind of will let me put it like this, right? Okay, so why is it not, okay. Image interpretation. So we have this this is a real picture. And the question is, how do we interpret this scene? What is the common sense of this scene? And one can say, you know, oh, it's weird enough to see a fish flying. But having an eagle riding on its back, that's really amazing. So, I mean,
Yeah, this is a very good example. This is a wonderful example.
right,
Yeah.
because how do you interpret this? And similarly, you can look at this picture here and ask, what caused the roof to break?
Yes, it was.
Of course, it's the cat that caused the roof to collapse, right? And
No, of course not.
but those two, I mean, they have to do with the common sense of the scene, and these could, to me, I think it's like the dog with the frisbee, because it is our background knowledge that tells us that fish do not fly. It's our background knowledge that tells me a cat cannot break a roof. So what we need here is some background information, background basic ground truth that we are. But with the dog, with the frisbee, it was the same, because I know that dogs usually don't stay on two legs. That if I see the dog on two legs, then it's kind of a very transient situation.
I see.
So the common sense here is about my ground truth, basic understanding of the world, which is like these two images here. But now I will show you a picture that is more like the other example of the kid with the sausage, which is a different thing. So look at this. Oh, where is my example now? Oh, here it is. So you see, we have here, this person is chasing that person, but the cameraman only sees this area here, and what looks in this area is that the left-hand guy is threatening the right-hand guy.
Oh!
And that's a question, that was the situation with the baby. It's a question of what part of the image are you focusing on. If I focus on this part of the image, then I have this picture, and it looks like the person in the left-hand side is threatening the one in the right-hand side. If I look at the whole image, then I see that this person is chasing this one. And that's more like what you had with the baby, with the kid and the sausage. The question of which part of the image are you paying attention to? Which is a different issue than what is my background knowledge about the world.
Yes, that's a different situation.
Right. So I wanted to emphasize that there are two different situations here. One is which part of the image do I pay attention to? And the other one, how do I incorporate my knowledge about the world?
Actually, I can also say that maybe there are the situations are the same. Because I'm seeing the eagle flying with a fish, but the knowledge is only a subsection.
But the knowledge,
the
the knowledge is not in the picture. The knowledge is, we know that fish don't fly. It's not in the picture. It's
if we have the whole world.
But I'm talking about an image. You are trying to analyze an image. What you are showing me is that the problem was that the deep neural network was focusing on the sausage, not on the face of the baby. Well, just I'm talking about the image. It's only the
I
image.
see, what's given, okay.
It's only the image, but where do you focus on? But the fish flying is not in the image. It's our prior knowledge that fish don't fly. So I'm saying that there are two issues here of common sense. One is common sense, the other one is which part is important and less important in the image. Okay, so that's my comment on your talk. So now let me go to the talk that I wanted to give.
Do you have any idea how we can model these?
I know, I saw it on Monday, and I just just thought about it overnight. It's not that I have a theory.
Okay.
But I'm just saying that the two, if you give this talk, be aware that you are really presenting two different examples. Okay, so let's go to the talk about clustering. Okay, so I'm giving you a talk that I gave. That I gave it.
At Oklahoma? Oh, this is AAA, I see, okay.
That was AAA. It was kind of they have something which is called Blue Sky Talks, where you can give a position talk. They invite you to give a position talk.
What's a position talk?
position about the situation, about some research area.
Oh, I see, okay.
What is your view of some research area?
I see, okay.
So I was invited to give this talk about my view on clustering. And it's a very kind of high-level talk, but that's okay?
Very
So-
good, oh, very good, that's exactly.
Okay, so I will just go through the talk, but really I want to, as you see, I really like to have a discussion. Okay, so of course we know that clustering is very important. We use it all over the space. I mean, I don't have to tell you, but what I claim is that we don't have theoretical understanding of what clustering is. That's my claim, that we don't understand clustering. And let me try to convince you that we don't understand clustering, and then we can talk about which direction should we go. What are the important questions that are not answered? So what do I mean by we don't understand clustering? So of course you have lots of analysis of a given algorithm. There's tons of papers on k-means, tons of papers on EM algorithm, tons of papers spectral clustering. But these are papers about a specific algorithm, not about the problem. And also you can do a lot of analysis of the cost function. I fix the cost function, how do I optimize it? There are lots of optimization papers. But the cost function is a choice that I make. It's not a definition of the problem of clustering. And also, we talk about, there's a lot of generative model. I mean, I talked to you last time on Monday or yesterday about mixture of Gaussians. Right? So you say, one thing to view clustering is say, I assume that the data was generated by mixture of Gaussians. I try to recover this mixture. So this is about assuming some generating model. But I want to talk about the essence. What are we looking for when we do clustering? These are only tools to achieve some goal. What is this goal? So to show you how much we don't understand it, I have here a copy from the syllabus of the basic machine learning course at Stanford. And they have a chapter about learning theory. And it's talk about bias variance trade-off, about union bound, Chernoff bias, visit dimension, and so on. You see, there's a lot of theory here, a lot of principles. The bias variance, the no free lunch, there are lots of principles here. Then they have a chapter about unsupervised learning or clustering. And what does it have? Clustering, mixture of Gaussian, factor analysis, PCA. There are no principles. This is just a laundry list of algorithms, a laundry list of tools. We talk about different tools without asking what are we trying to achieve. You see, there's a big difference between these two.
I used to do this sometimes.
Yeah. This is just a laundry list of tools.
Yeah.
This is a list of principles. And we don't have similar principles for clustering. I mean, this is the Stanford course, but any textbook in machine learning that you will take, and you compare what is happening in clustering is just a list of tools. So why is it problematic? So what are we missing here is some guidance. If you have a clustering task, which tool should you use for your task? And what I will try to convince you is that this is a very important problem. Because, you know, if you want to do sorting and you don't know which algorithm to use for sorting, what will be the difference between the algorithms if you do quick sort or you do heaps or whatever? One of them will be faster than the other. But at the end, both of them will give you the same sorting. But in clustering, it's not the case. In clustering, so given a concrete task, different algorithms will give you different results. So look at this clustering, for example. Here I have my data, and I want to cluster it. If I use k-means, 2 means, I will get this partition. This is one group, that's the other group. If I use single linkage, I will get this is one group, that's the other group. Right? Because you know what is k-means and what is single linkage, or should I explain it?
We know what K means is EM, it's single linkage, I don't know what a single
Okay,
linkage
so let me just, I'll use it as a good example. So single linkage is a family of clustering algorithms that are defined by a very simple procedure. So what is a procedure? We call it a hierarchical clustering algorithms. And the hierarchical clustering algorithms, they start at stage 0, every point, every instance is a cluster. And now we get stage K plus 1, or K is not good, K is the number of clusters, so say T plus 1, is we merge
nearest ones, I see.
some, clusters of T stage. Now the question is, how do we merge them? And then we need a stopping point. When do we stop? Because if we will not stop, then we will just end up with all the data in one cluster. So the hierarchical clustering algorithms, they differ in how they merge and when they stop. So how they merge, the single linkage, if you have different clusters, it defines different distance between clusters as distance between the closest points. So it will always, at every step, it will just merge the two clusters such that they have the closest points in the two clusters. But we can also talk about average linkage. That average linkage, for example, look at the average, the center of every cluster, and will now merge the two clusters that their centers are closest. That will be a different rule. Or we can talk about max linkage. That what we want to avoid, we want to make sure that we don't put together far points. So I look for every two clusters, I look at the furthest 2 points, and I will merge the clusters whose furthest 2 points are the minimal distance. So what I'm saying is that we can have different rules on how to merge. Single linkage always merges the ones that have the closest point. Right? And then, of course, we need to know how to stop. So here the stopping criteria was stop when you have two clusters. Or the stopping criteria could be stop when you have no 2 points which are closer than epsilon. Then stop. Or stopping criteria could be very different things. So those are hierarchical clustering. So if I take this data and I do single linkage, then I will start merging the closest points and then the closest clusters, and I'll end up with this one cluster here and one cluster here. Which for this cloud makes a lot of sense. But if I use k-means, I will get this partition. So what I want to emphasize is that unlike sorting, if I use different algorithms, I get results that are completely incompatible with each other. It's not just a matter of how much computation or small differences. It is completely different story. Now, if the data is so nice, two-dimensional, you can see it, then you can say, oh, in this case, this is correct. But what if you want to cluster data with 300 features? What if the data, what will you, right? Then there's a lot of difference between and you cannot just eyeball it and decide what's better. So how shall we do this job? So what I'm saying is that we can go back to the definition. What is the definition of clustering? The definition of clustering is partition the data set so that similar points reside in the same cluster and non-similar points get separated. That's basically what you want to get when you do clustering. But I'm claiming that those two instructions can very easily contradict each other. So here is an example where those two simple instructions are contradicting each other. So look at this situation. Look at the situation. Where is it? Here is my situation. Assume that this is my data. And what will I call close points? I will say close points are if their distance is smaller than alpha. And far points are points whose distance is bigger than beta. So now I want that every two close points will be together. Okay, so this point has to be with this point has to be with this point. If I want that similar points will live in the same cluster, what clustering do I get here? Yeah. What? One cluster. Everybody is together because I want that similar points will be in the same cluster. I can't cut it. But then I wanted that far points will not be together. And I got here far points that ended up being together. So I cannot satisfy these two requirements at the same time. By just following the requirement that every similar points will be together, I will end up with far points which are together, which I didn't want. Right? I mean, if you want to look at it abstractly, mathematically, it's because similarity clustering puts the group into equivalence classes. All the points in the same cluster is an equivalence class. But similarity is not an equivalence class. It's not transitive. If A is similar to B and A is similar to B and B is similar to C and so on, it doesn't mean that this point is similar to this point. We start with similarity or distance, which is not transitive. And we want to end up with the clustering, which is a partitioning. And partitioning is being in the same cluster is transitive. If A and B are in the same cluster and B and C are in the same cluster, then A and C are in the same cluster. So we have here an inherent conflict. And what I'm saying is that it is not the only inherent conflict that we encounter when we want to do clustering. Because you can also want other requirements. So for example, you want to balance cluster sizes. Maybe you don't want that there will be one cluster that takes 99% of the points and the other clusters share 1%. Or maybe you want, I mean, we talked here about joining similar points versus separating dissimilar points. Maybe you want that it's robust to outliers, the cluster. So what I'm saying is that we can view the different intuitive requirements for clustering as some kind of a graph where they are pushed in different directions. You cannot satisfy all of them simultaneously. And it's not just, I mean, you can think, okay, I came up with a very artificial example. But it's not just artificial examples. I mean, here are some real examples. Say, so single linkage makes sure that similar points will be together. Because single linkage each time merges two clusters if they have similar points between them. And max linkage, you see, you will never merge two clusters if their furthest points are far. So max linkage makes sure that far points will never end up together. So single linkage emphasizes similar points should be together. Max linkage emphasizes never put different points in the same cluster. And both of them ignore the size of the cluster. In both cases, you can get a situation in which, you know, you do single linkage and you get this is one cluster and this is another cluster, and there is no consideration to how big it is a cluster. So, for example, both are kind of ignoring the population size of the clusters. But k-means does take some consideration of balance between the sizes of clusters, if we do k-means. And there are algorithms that put more emphasis on balance. So what I'm saying is that if we look at this graph of conflicting requirements, we can see that each of the common clustering algorithms is kind of sitting somewhere in this balance. The single linkage say, I am here. very close to this corner. The max linkage say I'm very close to this corner. The k-means is somewhere here. And every algorithm is sitting...
That's a wonderful way to look at this thing. I
Okay.
understand this. That's, yes,
Okay.
yes.
And
That's a-
so,
What do you want in your domain, your task?
right, what do you want in your domain? That's exactly. So I want to give you examples where those different requirements are really affecting real-life considerations. So, for example, if you want, one of the clustering tasks that is important is the duplication of records in a database. So you have a database. Say I have a database of patients. I have a record of patients from different, and the records came from different clinics, from different hospitals. And I want to put together records that belong to the same patient. So it's a clustering task. All the records that belong to the same patient should be clustered together. Now, what do we want to emphasize? We want to emphasize that we should separate these similar points. Because it cannot be that someone whose feature vector is old and female will be saying it's the same patient as this other one which is young and male. So if I want to do, and that's a real problem in clustering, deduplication. Like we have Census Canada, that every year they take census of the people in Canada. But people move. So they want to know that the record of this person in Toronto is the same record of the person that was last year in Montreal. So they want to put, or you think of it, I mean, when you start doing the academic career, you look at Google Scholar, and you look at your papers. And sometimes you have different entries for the same paper. So you want to apply clustering that the entries that refer to the same paper will end up together. So these are called deduplication clustering. And clustering for deduplication, the main emphasis is that you want that these similar points will not end up as in the same cluster. You don't want to claim that dissimilar are the same. Okay? So here is an example where we want to emphasize don't merge far points. On the other hand, say I want to cluster people to predict the viral spread, say of disease. So now I know that if two people are close, the disease can pass between them. And the disease could, the cluster of people that are affected include people who are very far. Just because at every step the virus could jump because they were close. Or if I'm doing forestry, and I want to cluster areas of the forest, that if there is fire, they will catch fire together. So then I want to emphasize that similar points are together. Right? In the forest, all of those could catch fire together because the fire will go from one to another. So in this case of clustering for such purposes, for predicting the spread of a virus, for predicting fires, I want to emphasize a different thing, that similar points are together, which is opposite to this requirement. Or another example, say, I want to cluster neighborhoods for school districts. I want to say, all the kids in this neighborhood go to this school. All the kids in this neighborhood go to that school. Right now I want to cluster my city into neighborhoods. Now, balance is very important for me. Because I don't want one school to have 10,000 kids and the other school will have only 10 kids. So, you see, these are all real situations in which we use clustering. And each time we say, what should we do? Cluster. But people are not aware that they have different priorities depending on the purpose of the clustering. And you have different priorities, you have to use different algorithms, as we saw before. So that's kind of the message that I'm trying to convey. It is very important to be aware of what are the requirements of your application and what will this algorithm give you compared to another algorithm.
So are there those, the tetrahedron?
There's more.
There are more.
Yeah.
There are more.
There are more. They're just for the purpose of picturing it, I can have it to just 4 points, but there can be more requirements.
Oh, I see.
So one can ask, people use clustering all the time. How do they use clustering? So when I give this talk, I give this talk in different audiences, and people, like biologists or physicists, and they do clustering, and I ask them.
They do a lot.
They do a lot of clustering. I
We
ask
do a
them,
lot of clustering as
Right.
well, right.
okay, so which algorithm are you using?
Well, I think most students would use k-means or
Right, so I ask you,
spectral
right,
clustering.
why do you use this algorithm and not another one? And the answers that I get, the smartest people give you answers which are completely, I can give you some of the answers that I hear. How do you actually use it? So it's the most ad hoc manner. The answers that I get when I ask people, why do you use k-means? Then the answers that I get are things like, it's easy to use, no need to tune parameters. Or it is part of my software package. I'm using R, and in R I have command, k-means, very simple. That's why I use it. Or it's freely downloadable software. That's a good answer also. Or another answer that I get, it worked for my friend, so I use it the same. But maybe my friend had a different problem. You see, it reminds me of, both my parents are deceased now, but they were very old, and one time I come to my father to visit them, and I see that he's having a big bottle of Coca-Cola. And he never drinks Coca-Cola. So I asked him, why are you drinking Coca-Cola? He said, because I have a cold. So what's Coca-Cola have to do with cold? He says, oh, because my wife, my mother, she was sick a few weeks ago. She had diarrhea, and someone advised that she will do Coca-Cola to recover. So now he's using Coca-Cola to recover from a cold. But that's what you're using with clustering. You say, it was good for my friend, then I'll use the same algorithm. So it's like, it runs fast is an answer that I get a lot. So if I translate it to the medical domain, I don't know if I have it in my slides, it is like, my algorithm performs all other, it's just this medication is best, regardless of what your sickness is. Or you can say, here is an algorithm that can be implemented at linear time. It's just you come to the sick, take this pill because it only costs 99 cents. When we have to deal with our health, we don't use such considerations. We try to match the remedy to the problem. But when you use clustering, the smartest people, look at yourself. You ask them, why did you use this cluster? You answer like my father, because my friend used it and it worked for him. Or because it was cheap. Like easy download, I don't need to tune parameters, or runs fast, or whatever. And it makes a lot of difference at the end. So it's not like sorting algorithms, it will not make a big difference. But here it does make a difference, as we saw with the pictures. Okay. So, if you look at papers, look at ICML papers, NIPS papers, when they talk about clustering, they say, we check it on inherent data. Here is my data, on my data, see how my clustering went, let's look at the picture. But that's, of course, if your data looks like a collection of well-separated clouds, then it doesn't matter what you will use, you'll get the same answer. But real data does not usually look like floating clouds which do not touch each other. So, so if you have a clustering paper and you submit it to NeurIPS or ICML, and it's being rejected because you proved your point by an example, you can suspect that I was the reviewer. That's experimental evidence. So what I claim is for every two reasonable clustering algorithms, I can come up with data sets that will show you that algorithm A is better than B, and I can come up with different data sets that will show you that algorithm B is better than A. But that's what you see in the papers. Here is the data set, and here is my graphs, and here is my tables. See how I outperformed all the other tools. You outperform them because you pick the data that on which you outperform them. So, yeah. So that's what I mean by we don't have a good theory of clustering. We don't understand it well. So to turn clustering into well-defined tasks, we need to add some bias, we need to express our prior domain knowledge, we need tools to communicate between the purpose of the clustering and the algorithm that you pick. And we are having I can show you some of the attempts that we made in my group to answer this question, and we don't have a good answer, but I can show you my attempts. So, one attempt was axiomatic, like what we did so far. We're trying to formulate properties of clustering functions, like this function emphasizes close points should be together, and then translate the prior knowledge that you have about your problem, what is important in my problem. In the examples that I gave you, it was simple. Like for deduplication, it's important for you that far points will not be together. For spread of fires, it's important for you that close points will be together. But in many applications, it's not so easily translatable between your prior knowledge and the algorithm. So we were trying this approach. Another approach was we were trying this interactive, that we ask the user to provide some partial information about the desired outcome. So let me say a few words about each of those, and with that I will finish, because I don't have a definite answer. So the axiomatic property should look something like this. So I will have here a list of properties, different properties that I want. And here I can have a list of different clustering algorithms. And for every clustering algorithm, I can tell you which properties it satisfies. So there's some properties that all of them will satisfy, which I could call that's what defines a clustering. But they will differ in other properties. So ideally, you will be able to have such a table, and now the user comes, and you ask them which properties are important to you, and you look for a row in which the columns that are important to the user are plus. And that's how you pick your algorithm. I mean, ideally it looks very nice. The problem is that it's very difficult to use the same language, the language that we use for describing properties, that will make sense to the user. So that was kind of one approach that we went quite a while with it, but I don't feel it's really useful. So the problem is how to come up with properties that make sense to the clustering customer, or a language that bridges between the theory of the algorithms and the practical applications. That's a big challenge. And the other is kind of interactive. So what do we have interactive? I can ask the user questions. Like user can tell me, these 2 points must be together. Or these 2 points cannot be together. That's some kind of an extra information. Sometimes we call it semi-supervised clustering. It is partially supervised. You get some information about what is required from the user by telling you those should be together, those should not. Or you give them a clustering and they do a merge or split. They tell you these 2 clusters should be merged. This cluster contains things that should not be together, you should split it. Another option is that what we did is we analyzed the situation of sample clustering. So if we look in some situations, you can give the user a small subset. The user wants an algorithm because they do census data. It's very big. But you give them a small subset and you tell them manually cluster this subset. And from that I will try to learn, to infer what are your priorities. So we also did work on this direction. That how can you learn from the clustering of a small set that the user can do manually, how can you learn from that what will they want on the big data set for which they want an algorithm, for which they want to run a program. So, okay, I don't want to go into too technical. I mean, we have some technical results on all of these directions, but that's less important. So basically, the conclusions are that clustering should not be done without taking domain knowledge into account, and that we need a method to communicate the domain expertise in a way that's useful to the algorithm design. And we did two directions of attempts. One was the interactive setup, and the other one was the set of properties. But for none of them, I feel that we reached a solution. I mean, I had one of my students went out and did a startup for clustering, but I did not invest in a startup. I don't believe that's a real solution. I mean, okay, so that's what I wanted to tell you about clustering, and I'll be happy to discuss it further.
Well, this is, yeah, it's really thought-provoking. We have not looked into clustering problem. I've always had thoughts about it. There are many, many different, I mean, what's not mentioned here is how many clusters do you want it
Oh,
to
yeah,
be?
yeah. I have a whole outline of work and lectures about methods to choose the number of clusters.
Okay.
Because I only talked here about picking your algorithm. I didn't talk here about picking other parameters.
Yes.
Like there are other important parameters. How do you choose the number of clusters? How do you use the similarity over which you do the clustering? There are many other questions. I just wanted to demonstrate through this choice of algorithms. But we have papers on tools for choosing K. We have papers for how to choose a good metric that will reflect what you really want. With all important components of clustering.
Okay, well, students are thinking, let me just give you my thoughts. First of all, the linkage. I think it's, another word would be the agglomerative clustering. Okay,
Right.
so I think that was, you know, that's another one to
Yeah,
get.
it's a family of
Yes, okay, so that's what I wanted to
Right.
mention. The second one that really sort of got my thought going is, yes, you give, so you have a lot, I mean, you do clustering because you have a lot of data.
Right.
And you want to somehow group them to reduce the computation maybe, because you want to do processing, equal processing for each of the thing, or maybe do it in a sort of structured way. So I think that's
and that's
really
something that arises. I mean, I gave this talk several times in a context of health workers. And like doctors, they do, I mean, the last time I was talking in Bordeaux 2 months ago, and there was a doctor that is specialized in treatment of obesity in France. You don't see very fat people in France, but it bothers them. And he needs to decide for which patients he will advise a diet, for which patients he will advise some medication, for which patients he will do surgery of shortening the intestines, and this turns out that there's more than one surgery, different procedures. So he is grouping, he needs to do clustering in order to group his patients for the treatment. But he cannot express easily what are the properties of the clustering. He has some heuristic, and he knows that with the work with these heuristics, he succeeds for many patients. Few patients die, few patients do not lose weight for the short term. In the long term, everybody gains back the weight that they had. But yeah, so yeah, that's right. I mean, what he's doing, the clustering of patients, is in order to do the same treatment to every cluster.
Yeah.
But we don't know in advance
what will be the
right condition. Right.
But I mean, the last slide where you had, okay, so you have a massive amount of data, and I was thinking, yeah, if you could pick samples, some samples that's representative of the whole thing, but it's very distinct, and if you ask that person, some expert, the type of clustering that you want, and let's say that will be a good model to do the whole thing, I think that would be a very interesting thing.
Right,
Now,
so-
so the problem is,
How to
how do you pick?
Exactly.
How do you pick? So, we were
So
doing,
we were doing work on just what happens if I randomly pick points, and I randomly pick a small set of points, few hundred points, and give it to the user and tell them cluster these few hundred points. But that was randomly picking the points.
but I mean, I think that would be the barometer. If you can do selection, so there's an area called active learning. So we're looking at active learning,
Right.
okay? So how do you pick samples that would be a good representative of the whole thing, but it would be unique?
You see, if you look at for the deduplication, for example.
Mhm.
In the deduplication task, if I will take representative samples of different, they will all never be in the same cluster. Two representatives are never in the same cluster. But I don't want to output the clustering that tells me every point is its own.
Right.
Somehow, this notion of representative sometimes loses what you want to achieve with the clustering. Or,
Yes, I understand. So, you have different tasks, yeah, I mean, you showed various tasks with different prerogatives. And I think that's just giving a few samples and you give examples and do it. So how do you pick those samples? If you can formulate a mathematical way so would samples that represent the distribution of the whole thing, representative, I mean, what do you mean by representative?
What do you mean by representative? I mean,
And-
sometimes what we do, because it just translates the problem to, in what way do you want to represent the data? What
Yes.
is representative?
Yeah,
I mean, if you think the deduplication is a very good example that kind of, usually it's a counterexample to every suggestion that I get. Because it is so different. What do you, I mean, you have.
So it's the same value, deduplication means you have to,
You have similar values.
Similar values, but they're
Right.
far away, right?
Yeah. And you don't even, I cannot even tell you what is the number of clusters, because I don't know. If I look at my Google Scholar, I look at my list of papers, and I know that Google Scholar made some mistakes and have the same paper several times. But I don't know how often it happened. I don't know in advance how many single papers should be there. Or if you records of patients from different clinics, you don't know what's the number of cluster patients. So yeah, the problems are really difficult, and trying to pick some representative and do the work on the representative is a reasonable option, but how do we define the notion of representative? And my basic philosophy when I do machine learning is the need for prior knowledge, the need for domain expertise. What will be similar patients for the doctor that wants to fight obesity will be similar patients for the doctor that wants to fight flu. Because
Yeah, so I think, just one thing that we could probably collaborate on this. So you had two attempts. One was looking at various, you categorized your algorithms, and then you also categorized various conditions or requirements, right? So for a subsection of the requirements, mathematically stated, how do you sample so that it represents the whole thing, so that you get, so let's say you start out with some known cluster, with good cluster, and then you somehow have this whole thing, and then
so
how do you get it?
what we try to do in that, I would also like to hear the students.
Yeah, please. Yes,
I'm really curious what you think and what your thoughts are.
뭐 혹시 뭐 얘기하는 거? Joshua, you want to say something? You hear that? No? Anybody?
I
Yes.
have a question. So you mentioned that when we choose an algorithm, we need to base on some biases.
Right.
But those algorithms in the examples, it's just very like conventional methods. So recently there are some like deep clustering methods which can embed the observation into some latent space, which may be presented in some space that
Feature space.
feature space that the cluster are well separated. What do you think about like we train some like conditional embedding?
Right.
The condition is the biases that you mentioned, and then it can somehow embed into the
Right.
feature space. Then
No,
you can
right.
use any like conventional
Yeah, so,
method.
so I think what you're hinting at is a very important, an important point is that I could give this talk, I gave this talk from the point of view of saying the data is given to you, the distance isn't given to you, I gave you pictures of it, and now you have to pick an algorithm. But often in reality it's the other way around. The data, you can embed it in different ways. And I can say, I will always do k-means, but with different embeddings of the data, k-means will give me different results. And now instead of choosing an algorithm, I have to choose a representation of the data. You see? Because it's very easy to give examples like this. Right? If a representation of the data is in polar coordinates, then points which are along the same array will look similar, even if they are in Euclidean distance far. So we can look at the problem differently by saying, let's fix a flexible enough clustering algorithm, but what we are going to adjust to the user requirements is the notion of representation, or the notion of a metric. And this allows us to do more kind of smooth analysis, because metrics are something that you can talk about convexity, you can talk about gradient descent, improving your metric, which you cannot talk about when you are picking an algorithm. I cannot do gradient descent and get from k-means to single linkage. So we often, when we try to handle it, we really turn the problem into searching for a good metric. But the choice of metric or the choice of embedding depends on your application. So that's saying it's a deep neural network doesn't solve the problem. Because it really is, what is the objective that you are training the deep neural network with? And for different purposes, you will get embedding, you'll get good embedding with neural network if you chose the right objective when in your training.
I want to follow up on your question and Shai's comments. Once you're done with your task right now, what you're working on, maybe you want to work on this. I think very interesting. Let's say I fixed my algorithm to k-means. Okay, I fixed my algorithm to k-means with I fixed it with
you need some other on top of it some.
Yeah, no. So let's just say k-means and let's say some number of clusters. And let's say you have data. You want to transform that data, okay, by some network, transform it so that k-means will give you, the output of your k-means will give you the best performance on the task.
Yeah, we have a paper, UAI 15, that took exactly this approach. So me and the student in, I think it was UAI 15, we had a paper that was taking this approach. We fixed k-means, and now we are trying to learn the metric over the data.
Okay, so this is going to be a little bit more current. We do a lot of embedding, so we have the word embedding. Okay,
Yeah, embedding and metric are similar.
Yes. Embedding in a certain way Okay, what, I know that you're doing a lot of RL, and then you have a lot of, what do you call, history, right? History, lots of history. Maybe you want to cluster those histories in a certain way. So, in terms of embedding is, let's say, embedding in a certain way such that when you cluster that, you get the best performance for a specific task. I think that will be a very interesting, and maybe we can also go back, go on your paper in 2015.
Yeah.
I think that will be sort of an interesting.
Right. I mean, I worked for a few years. I think for almost 10 years, I worked on different tools for incorporating prior knowledge in clustering, and then we moved on to other things. I felt that, yeah, I mean, I've exhausted myself on that. But the problem is still open, and it's still very interesting to come up with ideas.
Yeah. Do you think that the future direction? Do you think that the future direction is that we will delegate the burden of selecting the algorithm to the learning feature instead of like developing various algorithms for various like biases of the problem?
What is your view on that? So
what is your view on the future direction of clustering? So my view is that I think that future will be like delegating the burden of selecting algorithm. Instead of inventing new algorithm for clustering, we will delegate the burden into the learning feature.
To learning the features. But we can all. Another interesting question is, if you fix the algorithm, do you have enough flexibility just by changing the metric? Do you have enough flexibility to get all possible results? Maybe, I mean, we have work on saying if you fix an algorithm, it also restricts the type of result that you will get, regardless of what the metric is. It's another interesting question. But definitely there is a lot of space to go in just choosing a good embedding. I agree. But you have to be aware that by fixing the algorithm, you already, in some way, tying your hands. Because we have work on this, on saying what are the limitations of an algorithm, of a given clustering method, no matter what the metric you fit it with.
Thank you.
Yeah, but the questions are open and important. If you have ideas, it would be great.
Shim or 관영? 웃음이 나오는데, do you have thoughts?
No, that's usually they say, don't be shy.
Any Tum? No? Thinking about it? Okay.
Yeah, I'm still here tomorrow, and I'll be happy to talk to you tomorrow. We don't have to come up with questions on the spot. But I'll be really happy to. I mean, tomorrow I'm giving a talk in the morning, right?
Right.
But then I'm here for the rest of the day, and I'll be happy to talk.
Thank you very much, and I think it's wonderful. Okay, so that concludes our sort of internal talk. I mean, I think it's always, it's been an inspiring experience for me to talk with Shai. I mean, I always thought, he's a wonderful man with, I've also found that he's very compassionate and full of thoughts and lots of experience. I really thought about picking his brain for all aspects, but I mean, thank you very much. Let's give Shai a big hand.